In approximately 4.2 billion years, our Milky Way galaxy is destined for a direct collision with its closest and largest galactic neighbor, the Andromeda Galaxy. This prediction of an impending galactic encounter is substantiated by decades of meticulous astronomical observations and sophisticated computational modeling. Notably, in a landmark 2012 paper, detailed measurements from the Hubble Space Telescope precisely confirmed Andromeda's collision course with the Milky Way. This future collision presents a fascinating paradox. How can two massive galaxies be on a collision course when the universe itself is generally understood to be expanding, causing galaxies to move away from each other? The Andromeda Galaxy has been observed for centuries, though its true nature was understood only relatively recently. The earliest known record of Andromeda comes from the Persian astronomer Abd al-Rahman al-Sufi, who described it in his Book of Fixed Stars in 964 AD as a small cloud. This marked it as one of the first nebulae to be identified. Later, in the 17th century, European astronomers like Simon Marius and Charles Messier independently observed and catalogued it. Messier included it as M31 in his famous catalogue of nebulae and star clusters in 1764, primarily to distinguish it from comets. For a long time, Andromeda, like many other spiral nebulae, was thought to be a gas cloud within our own Milky Way galaxy. The true significance of Andromeda became the subject of intense scientific debate in the early 20th century, famously known as the Great Debate of 1920 between astronomers Harlow Shapley and Herbert Curtis. Shapley argued that spiral nebulae were smaller gas clouds within the Milky Way, while Curtis contended that they were island universes, separate galaxies far beyond our own. The definitive proof came in 1925, when Edwin Hubble, using the powerful 100-inch Hooker telescope at Mount Wilson Observatory, identified individual Cepheid variable stars in Andromeda. Cepheid variables have a known relationship between their pulsation period and their intrinsic luminosity, allowing astronomers to calculate their distance. Hubble's measurements showed that these Cepheid stars, and thus Andromeda itself, were far too distant to be part of the Milky Way. His calculations placed Andromeda millions of light years away, firmly establishing it as a separate galaxy. This discovery revolutionized our understanding of the universe, proving that the Milky Way was just one of countless galaxies and greatly expanding the known scale of the cosmos. Andromeda's identification as an island universe was a pivotal moment in cosmology, laying the groundwork for the modern understanding of an expanding universe filled with billions of galaxies. This groundbreaking realization about Andromeda's distant nature was, in fact, a crucial precursor to an even grander discovery, the expansion of the universe itself. The idea that the universe is expanding is a key part of how we understand the cosmos today. It started with Edwin Hubble's discovery in 1929. He noticed that galaxies are moving away from Earth, and the farther away a galaxy is, the faster it moves. This relationship is called Hubble's law. This isn't like galaxies flying through empty space. Instead, it's space itself that is stretching, carrying the galaxies along with it. As space stretches, the light from distant galaxies also stretches to longer wavelengths, which is what we call redshift. This redshift is a direct sign of the universe expanding. The idea of a future collision between Andromeda and the Milky Way has a long history in astronomy, evolving from early speculation to scientific certainty. For over 50 years, astronomers have known that the Milky Way and Andromeda were on a collision course. This early understanding was primarily based on Andromeda's blue shift, which indicated it was moving towards us at about 110 to 120 kilometers per second. Additionally, the timing argument, pioneered by Kahn and Vulture in 1959, suggested that these two massive galaxies, having formed close together in the early universe, were gravitationally bound and would eventually reverse their initial separation caused by cosmic expansion to approach each other. However, despite this knowledge, the precise details of their future encounter were poorly understood, and it was not definitively known whether a collision was certain. The challenge lay in measuring Andromeda's proper motion, its sideways velocity across the sky. While its direct approach, or radial velocity, was easily determined by blue shift, the lateral speed was extremely difficult to measure with sufficient precision to draw firm conclusions. A significant sideways motion could mean the galaxies would merely graze each other, or even miss entirely. The definitive conclusion that the collision is sure to happen came in 2012. This breakthrough was made possible by the Hubble Space Telescope. Between 2002 and 2010, a team of researchers led by Roland van der Marel at the Space Telescope Science Institute conducted extraordinarily precise observations. They achieved this by tracking the minuscule shifts of individual stars within Andromeda against the seemingly fixed backdrop of much more distant background galaxies. This technique allowed astronomers to measure Andromeda's tangential velocity with unprecedented accuracy. The crucial finding was that Andromeda's sideways motion is very small given the observational uncertainties. This result removed any doubt, confirming a highly probable direct collision course. Further refinement of these measurements has been provided by the European Space Agency's GAIA mission, which is designed for ultra-high precision astrometry across the Milky Way, has also contributed to measuring Andromeda's proper motion, yielding even more accurate velocity estimates that are consistent with Hubble's findings and reinforce the certainty of the merger. This leads us to the core explanation for why Andromeda is on a collision course with the Milky Way. Despite the universe's overall expansion, gravity overwhelms expansion on local, gravitationally bound scales. There is a universal tug-of-war between the force of gravity and the expansion of the universe. While the fabric of space-time expands on cosmological scales, causing distant galaxy clusters to recede from one another, the immense gravitational force exerted by dense concentrations of matter can counteract and locally overcome this expansion. To understand this, it's crucial to distinguish between the large-scale expansion of the universe and the behavior of structures on smaller scales. Cosmic expansion is predominantly a large-scale phenomenon, primarily observed between galaxy clusters and superclusters. At these immense intergalactic distances, the gravitational attraction between celestial bodies is generally insufficient to counteract the stretching of space. Consequently, these vast structures recede from one another in accordance with Hubble's law. However, on smaller scales, the internal forces at play within systems are overwhelmingly stronger than the subtle stretching effect of cosmic expansion. For instance, within our own solar system, the sun's powerful gravity binds its planets, preventing them from being stretched apart by cosmic expansion. Similarly, individual galaxies such as the Milky Way and Andromeda are coherent structures where billions of stars, vast clouds of gas and dust are held together by the galaxy's collective gravitational pull. The galaxy itself does not expand. Rather, its internal gravitational forces maintain its integrity. On an even larger scale, galaxy groups and clusters represent collections of hundreds or even thousands of galaxies whose mutual gravitational attraction is strong enough to keep them bound together, effectively decoupling them from the general Hubble flow. This means that the gravity connecting the galaxies within such a system is enough to overcome the effects of dark energy, which normally causes galaxies to accelerate away from one another. In this sense, gravity dominates at smaller distances while dark energy dominates at larger distances. The Milky Way and Andromeda galaxies are prominent members of such a gravitationally bound system, known as the local group. This group, characterized by a dumbbell shape with the two large spirals and their numerous smaller satellite galaxies, is a prime example of a cosmic structure where gravity reigns supreme over expansion. Because the Milky Way and Andromeda are gravitationally bound within this system, their relative motion is dictated by their mutual gravitational attraction, not by the overall expansion of the universe. They are, in essence, falling towards each other within their shared gravitational pull. Even though the local group is held together by gravity, it's also part of a larger cosmic structure called the Virgo supercluster. The immense gravity of the central Virgo cluster does exert a subtle pull on our local group, slightly slowing our recession from it. This illustrates that gravitational influence operates across multiple scales, even if the local group's internal dynamics are mostly controlled by the pull between its main galaxies. Understanding this interplay of forces sets the stage for predicting the long-term consequences of Andromeda's approach. The interaction between the Andromeda and Milky Way galaxies will happen over billions of years. Scientists have used complex computer simulations to predict the different stages of this process. As Andromeda first approaches, its disk will gradually look bigger in our night sky. This will become noticeable in about 2 billion years. Around 3.75 billion years from now, Andromeda will appear to fill our view, and its gravity will start to pull and distort the Milky Way's spiral shape. The first close pass, expected around 3.85 to 3.9 billion years from now, will be a significant event. As the galaxies pass through each other, their gravity will create long tidal tails, pulling streams of stars and gas out into space. This squeezing of gas between stars can lead to more new stars forming, which we would see as bright clouds of gas and young star clusters. After this first pass, around 4 billion years from now, both Andromeda and the Milky Way will look stretched and warped. The galaxies will then swing back for a second close encounter about 5.1 billion years from now, with their central parts looking like two bright blobs. By this stage, fewer new stars will be forming because most of the gas and dust will have been used up in earlier star formation. The final merger, taking place around 7 billion years from now, will see the two galaxies completely join and reshape into a single, huge, oval-shaped galaxy known as Milkomeda or Milkdromeda. It's important to understand that even though we call it an interaction, actual star-on-star crashes are very unlikely. This is because there's a huge amount of empty space between individual stars and galaxies. Galaxies are mostly empty. The interaction is mainly about gravity, leading to a complex process where tidal forces change the shapes of galaxies, alter the paths of stars, and compress gas between stars. This gravitational interaction, not direct impacts, is what will fundamentally shape the new merged galaxy. Our Sun and solar system are not expected to be destroyed. However, their path within the new Milkomeda galaxy will change. Simulations suggest there's a 50% chance that our solar system will move 3 times farther from the new galactic center than it is now, and a 12% chance it could be completely thrown out of the new galaxy. There's also a small chance that the Sun might become more gravitationally linked to what's left of Andromeda than to the Milky Way before the final merger. At the center of both the Milky Way and Andromeda are supermassive black holes. During the merger, these two black holes will slowly spiral towards each other. This happens because of dynamical friction, where gravitational interactions with nearby stars cause the black holes to lose energy and get closer. Once they are about 1 light year apart, they will start to strongly release gravitational waves, losing more energy until they completely merge. This final merger of the supermassive black holes could create a very bright quasar or an active galactic nucleus, releasing a lot of energy. Regarding how new stars form during the merger, while galaxy mergers often lead to more star formation, the Andromeda-Milky Way interaction is expected to have only a modest increase in new stars. This is because by the time of the merger, there will likely be less gas left in the disks of both galaxies, and this gas is what new stars are made from. This shows that the outcome of mergers can vary and depends greatly on how much gas the interacting galaxies start with. While big mergers can cause bursts of star formation, overall star formation in galaxies like the Milky Way is often driven by internal movements, and not all increases in star formation are directly linked to mergers.